have to admit to all of you that certainly standing here in front of you, I do not look like your normal impression of an astronaut. So you're going to have to take my word for it that this was me back in December of 1993 when we rescued and repaired the Hubble Space Telescope. That is not what I'm going to talk about today, although I will certainly be happy to answer questions later on. What I really want to talk to you is about an experiment which has taken the last 10 years of my life. I never actually believed that I would be involved with Mars. You know, when I first became an astronaut back in the late 1970s, it was just 6 years after the last Apollo mission to the moon. And we were very optimistic. We thought, oh, pretty soon we're all going to be going to Mars. We'll get back to the moon. Well, that has not happened yet. But I was fortunate enough to be involved with this experiment, which ultimately will make it possible for humans to explore the red planet. So let's review a little bit about the history of humanity's knowledge of the planet Mars. Obviously, we have known since ancient times that there was something special about Mars. It was the red planet, the god of war, and so on. It was not until the 1960s and the dawn of the space age that we made the first flyby of Mars, and the pictures that came back were very disappointing. People had imagined all sorts of possibilities for life on Mars, but in fact, the first pictures that came back, it looked very much like the uninhabitable parts of the moon. Well, fortunately, we persevered, sent several other missions, discovered that Mars is a very varied planet. There are parts of Mars which look like this, like parts of the moon, parts of Mars that look like deserts, and eventually, in an attempt to look for life on Mars, in 1976, we sent the two Viking probes which landed on the desert. Now, frankly, we know now that this was not a good place to look for life on the surface because it is bathed in radiation, ultraviolet, cosmic radiation, and in fact, Viking did not find any life on Mars. And that kind of led to a lack of interest for quite a long time. But that interest picked up again when in 1997, I think it was, we sent the first of a series of rovers. This was the small Sojourner rover, followed later on by the wonderful Spirit and Opportunity rovers, and then Curiosity, a much larger rover, and this is the same size roughly as the Perseverance rover, which carried the MOXIE experiment. And this has given us a very different picture of Mars. More and more that we have found out, it looks like there has been a period on Mars when there was a lot of water on the surface. We see evidence which, you know, if we see landscapes like this on the Earth, there's no question that is a river system. Now, you have to be careful. Just because you see something on Mars that looks like something on Earth does not necessarily mean that it is exactly what we have on Earth. But nevertheless, the more we look, you look at the faces of cliffs, and as the seasons on Mars change, we see the different colors as though some liquid is percolating out of the ground. And then an earlier rover discovered what we call the blueberries. These are little spheres of the mineral hematite. And hematite on Earth only forms underneath salt water. So the evidence is really overwhelming that there were periods on Mars where there was significant water. Now, how could that be possible? Right now, the atmosphere of Mars is very thin, only about 1% of the density of sea level atmosphere on Earth. It's about the density of the Earth's atmosphere 30 kilometers above the surface. At that pressure, liquid water does not exist. It just evaporates or turns to ice. But we know there are some very, very large volcanoes. In fact, the largest volcano in the solar system, Mons Olympus on Mars. The early volcanoes on Earth spewed out enormous quantities of carbon dioxide. And we believe that this happened on Mars. Mars, in the early part of the history of the solar system, we believe, had an atmosphere of carbon dioxide. And that carbon dioxide, just like here on Earth, led to global warming, so that the surface on Mars was not only had sufficient pressure, but had the right temperature to support liquid water. There are evidences of a seashore around the northern hemisphere of Mars. The northern hemisphere is actually lower than the southern hemisphere of Mars. Now, we don't know if there was really a full ocean like you see here, but all the evidence points to a time on Mars when there were significant amounts of water. We don't know exactly how long that water lasts. There's a lot of questions that we still need to answer. What happened to Mars? Well, the sun periodically puts out enormous emissions of charged particles. When these hit the Earth, you can see they are deflected by the Earth's magnetic field. And so we're more or less protected from the onslaught from the sun. But remember, the Earth's magnetic field is sustained, we believe, by a rotating magnetic core deep inside the Earth. And we believe that early in the solar system, Mars also had this kind of a rotating liquid magnetic core. But Mars is a lot smaller than the Earth. It cooled off a lot faster. And so the current hypothesis is that that magnetic field collapsed as the iron core solidified. Mars no longer had a magnetic field to protect itself against the onslaught of solar radiation. And of course, Mars is smaller than the Earth, so it has less gravity to hold on to the atmosphere. And so eventually, Mars lost most of its atmosphere and is now the cold, dry desert that we know as the red planet. But let's remember, back in the very early history of the Earth, almost as soon as liquid water was able to form, we now believe that single-cell life evolved very quickly, almost as soon as conditions allowed. And so there is this fascinating question: did life ever evolve on Mars? That's something that the Perseverance rover, which carried our MOXIE experiment, was designed to look for. Now, I'm not going to talk about the search for water or life on Mars by Perseverance. It's an ongoing process. What I would like to talk about, though, is this experiment, which hopefully will make it possible someday for life to exist on Mars once again, human life. If you want to look for evidence of past life on Mars, probably the best way to do it is to drill. The European Space Agency has the ExoMars experiment. We had hoped to have it launched a few years ago. There were problems, but it will be launched on a NASA rocket in another year. And that will be able to drill about 2 meters down. We haven't found any liquid water near the surface of Mars. Maybe ExoMars will be able to find something, but I suspect that if we really want to explore Mars the way it should be explored, we're going to have to drill much deeper. And frankly, robotic drilling is very difficult. If you know anything about drilling for oil, you constantly have to change the drill bits. It requires someday oil rigging roughnecks on the surface of Mars. So now we're talking about sending people to Mars. Now, I don't know how many of you in the audience have seen the movie The Martian. The big question was, how are we going to get Mark Watney back from Mars to the Earth? So you all saw, if you saw the movie, you know there was a big adventure. He learned to grow food. He made his way finally to a rocket which had been left in place and fueled up with fuel and oxygen for another crew, which was going to come in a few years. Mark Watney got on that rocket, and sure enough, he got off the surface of Mars. Very exciting. But what they did not tell you about in the movie was, where did all that propellant come? It takes an awful lot of propellant to lift a rocket. That rocket was built for 6 people. Now, I'm in the Department of Aeronautics and Astronautics at MIT. We know how to build rockets, and we know how to calculate how much propellant it takes to get you and a rocket for 6 people off the surface of Mars. You need about 40 metric tons of propellant. It'll probably be methane and liquid oxygen. 3/4 of the weight of the propellant is oxygen. We're talking about 30 tons of oxygen. Now, here's the deal. To get 1 ton of anything to the surface of Mars, launching it from the Earth, you need to put about 15 tons of something into Earth orbit. Most of that is propellant, but you also need the rocket body, the rocket motors, the heat shields. So if we're talking about getting 30 tons onto the surface of Mars, we're talking about putting 450 tons into Earth orbit. Now, just to give you a sense of what that means, a Saturn V rocket or NASA's new Space Launch System could take about 120 tons into Earth orbit. So we're talking about 4 launches of a Saturn V, each one of which cost $1 to $2 billion. That's a lot of money. Wouldn't it be great if we could make the oxygen on Mars rather than have to bring it from Earth? Now, many things, if we ever are going to explore Mars, many things we're going to have to bring from the Earth. Anything that's manufactured, spacesuits, computers, and anything. We don't manufacture things on Mars, at least not now. But dumb old oxygen? I mean, if we could bring that oxygen from Earth, we have saved a lot of money, and that is what is behind, we call it ISRU, in situ, which means in place, resource utilization. Essentially, what that means is we learn to live off the land, which is what explorers have done since time immemorial. If you're crossing the ocean and you come to an island, you stop at the island and you get more food, you get water. We can do that on Mars, but we have to learn how to get the oxygen on Mars. And that is what MOXIE is all about. Now, there are several ways that you can get oxygen. The Phoenix lander, which had it was not a rover, it was just a lander. It didn't move around, but it did have a scoop. And it was able to go through the first top few centimeters of the Martian regolith, and underneath there was ice. We know there is a lot of water on Mars, and you can take that water and you can electrolyze it, just like everyone here in high school has electrolyzed water. You get hydrogen and oxygen. The problem is The ice that we have found on Mars is way up in the northern latitudes, and people are liable to go close to the equator. So while it's possible to mine the ice, you really have to set up a mining operation. You have to transport the ice, electrolyze it. It's a very complex process. Someday, I'm sure we will be doing that. But in the meantime, the nice thing is the Viking lander confirmed that Mars does have a very thin atmosphere that is almost entirely carbon dioxide, carbon, oxygen, CO2. And that's what MOXIE is all about. Mars Oxygen ISRU, which you now know what it means, experiment. So that's our acronym. What does MOXIE actually do? We want to make enough propellant, oxygen, to use as a rocket propellant. Most people, when I say we're making oxygen on Mars, oh my goodness, I see sunshine out there. Well, that's very welcome. Excuse me for the interruption, but it's, anyway. Most people, when they hear that we're going to make oxygen on Mars, they say, oh yeah, you need to breathe oxygen. Well, no question, if I were on Mars, I would want oxygen to breathe. But I only breathe less than 1 kilogram of oxygen every day. That's going to be a long time before I need 30 metric tons of oxygen. But if I want to come home from Mars, which I think I would if I were there, that's what we're really interested in with MOXIE, is to develop a technology that will allow us to produce large amounts of oxygen. Now, MOXIE is just a demonstration of the technology. This is a printed version of the MOXIE experiment, just to give you a sense of the size, just very small. Not designed to power a rocket. Again, it was designed to verify a technology which we tested many times on Earth, as you can imagine. MOXIE was tested in Mars-like environments, which we can create in laboratories. But NASA has a rule. If you develop any technology or piece of equipment that is mission and life critical, and certainly making oxygen is life critical, you don't just have to demonstrate it in a Mars-type laboratory on Earth. You need to demonstrate it in its real environment, which means we had to show that the process works on Mars. We fully expected it to work, but you never know. Maybe Mars had some surprise that we never thought about. And so that's why we sent MOXIE to Mars. This is the actual inside of the experiment, and I'll explain to you a little bit later how it actually works. But just by way of a preview, we have a compressor which pulls in and compresses the Mars atmosphere, and we put it into an electrolyzer because it turns out, just like electrolyzing water, you can electrolyze carbon dioxide. It's just a lot more complicated. And of course, as an experiment, you need lots of sensors, controls, and I'm not going to go into a lot of the technical details. But once you launch something to Mars, it's hands-off. Everything has to be autonomous. If something doesn't work, there's not a whole lot we can do about it. So as you can imagine, before we launch, when we're developing the experiment, we do a tremendous amount of testing in the laboratory. Eventually, you turn your experiment over to the rocket people. Here you can see MOXIE being lowered into the Perseverance rover. It doesn't look much like a rover now. They hadn't put the wheels on yet, but eventually it got wheels, it got all the other experiments, and you then pack it up. You can see here is the heat shield, which protects it from the re-entry heating in the surface of Mars. There's the rover all folded up, the back shell, and that up at the top is what we call the cruise stage. That provides all the guidance and control and propulsion while you're on the way to Mars. You get rid of that before you get to the Mars atmosphere. We launched in July of 20. beautiful launch. And here's where we decided to go. Now, remember, as I said, one of the basic goals of the Perseverance mission is to look for signs of ancient life on Mars. Obviously, we don't know if life ever evolved, but unless you look for it, you're never going to be able to answer the question. And so they chose a place on Mars. You can see this looks like an ancient river and a river delta, which happens to be made of minerals which, at least here on Earth, are well known to be able to preserve fossils. So if there was ever single-cell life on Mars, perhaps some of it got washed by the river and is located in the delta. So that's where we decided to go. But when you look around, there's a lot of nasty territory around here, places where you would not want to land. And so there were very, very tight constraints, much more than in any previous Mars mission, on the accuracy of landing of the Perseverance mission. Landing on Mars is really difficult. It's the worst of all worlds. When you come to land on the moon has no atmosphere, so it's just rocket propulsion all the way down to the surface, like we did with Apollo and all the experiments which we've landed on the moon. When you re-enter the Earth from space, the Earth has a very thick atmosphere. Up at the top of the atmosphere, maybe 60, 70 kilometers, we go through an intense heating phase. The atmosphere is very thin, but you enter it very fast. You heat up, so we need heat shields. But when you get down into the lower atmosphere, it's thick enough so that you can land with a parachute or with wings like the space shuttle did. Mars, on the other hand, as I say, it's the worst of all possible worlds. It has a thin atmosphere, so you have to go through all of the re-entry heating problems that we have when we enter the Earth, but the atmosphere is too thin to land with a parachute. We do use a parachute, deploys at about 3 times the speed of sound, which is no easy task. But the atmosphere is too thin. If you rode that parachute all the way down, you would hit the ground so hard that you would be destroyed. So eventually, you have to get rid of your parachute and come down with rocket propulsion, just like we land on the moon. So as I say, it's the worst of all possible worlds. How were we able to land so precisely, more precisely with this mission than any previous mission that's ever been to Mars? A new technique which NASA developed called terrain relative navigation. The way you do it is when you're still under the parachute, you take a picture of the ground and loaded into the memory of the onboard computer is a picture of that same part of the ground taken from orbit. The computer then compares the 2 pictures and it's able to figure out exactly where it is. It updates your inertial navigation state, and that allowed us to achieve the accuracy of Mars landing that was required. This is, I hope you've seen some of these pictures, but pretty incredible, the photographic coverage they had of this mission, where there was a camera on the sky crane, which basically had the rocket propulsion, which lowered the Perseverance rover to the ground. And then the Perseverance rover had cameras looking up at the rocket stage. Notice, by the way, you don't see any fire coming out of the rockets. They always, when they draw pictures, they always make fire coming out. But with this kind of propellant, you can't really see it with the naked eye. But anyway, we nailed it. We landed right near the delta, exactly where we were hoping to. And now we're on the surface of Mars. You can see here is the edge of the delta. And beyond that is the edge of the crater. And in fact, after almost 3 years of operation, Perseverance has explored the bottom of the crater. It spent about 2 years on the delta collecting samples which eventually, I hope, will be brought back to Earth, although NASA is still trying to figure out how to do that for an affordable amount of money. But that will be incredibly exciting. It's bringing back samples from Mars has been on the very top list of planetary astronomers for decades now. Perseverance is collecting samples, leaving them eventually to be brought back to Earth. When, I don't know. But in any case, this is the actual rover. I'm not going to go into all the detail of all the different experiments. Most of them are designed to look at the geology and eventually figure out if anything that we're looking at is conducive to preserving evidence of previous life. There is a weather station, the MEDA, which is a Spanish experiment. It's international. The SuperCam is from France. Incredible experiment. They can actually fire lasers at rock, and then they have a spectroscope which analyzes the vapors. And then the RIMFAX Norwegian experiment, for the very first time, a ground-penetrating radar on Mars. And so as Perseverance moves along the surface, we can analyze the substructure of the stratigraphy. And if there does happen to be any underground water or ice, RIMFAX could see it. So far, no joy. And then MOXIE, which you cannot see because almost all of it is inside the rover. There is Mars. As I say, Mars does have a very thin atmosphere. Almost every day we observe dust devils, which you can see, little, gyrating particles. There's lots of dust in the Mars atmosphere. It's very interesting how a rover is operated, because there's a team of scientists who wants to use the rover to look at interesting places on Mars, but there's also a team of engineers who are responsible for operating the rover safely. So just as an example, let's say you're a scientist, you look up there, oh, look at that line up there. What caused that? That's very interesting. We would really love to go and look at that more closely. And then the engineers look at these big rocks in front and they say, no way, you're not going anywhere near there because, the rover, this is a problem. You get the rover stuck and there's nobody to dig it out. And so there's a constant interplay between the rover drivers and the scientists. By and large, we are able to go to a lot of interesting places, and there are, however, places which you can't get to. What's on the other side of those hills? And, too far for the rover to go. So for the very first time, and I'm sure all of you are aware of this and hopefully have seen pictures, but we took a helicopter to Mars. Now remember, the atmosphere at the sea level of Mars is like 30 kilometers above the surface of the Earth. We don't fly helicopters that high. We can't do it. So it was an extraordinary development, what they did. We dropped that little helicopter, it unfolded, drove away, and it was originally only supposed to make 5 flights. And after this 5th flight, it was just they were going to send it off to who knows where. But it worked so brilliantly that it actually, over several years, made 72 flights. And remember, there it is. Nobody's joysticking that in real time. All of this has to be pre-programmed. It's all autonomous. It's just an extraordinary development. And NASA is now working on developing much larger and more capable helicopters. There it is going up. And remember, everything has to be autonomous. It has to look for a safe landing place every time it flies. Unfortunately, on the 72nd flight, didn't have such a good landing. It broke one of the rotor blades, and so that was the end of the life of the Ingenuity helicopter. Let's go back to that historic day, April 19th of 2021, when we had the very first flight of Ingenuity. All it did was to go up 5 meters, turn back and forth, and land. But that was history. It was a Wright brothers moment, the first controlled, powered flight of an aerodynamic vehicle in the atmosphere of another planet. Absolutely spectacular. And the next day was also historic because for the very first time, we produced oxygen on the surface of Mars. I wish that oxygen were as photogenic as the helicopter. Unfortunately, you can't see it, and so all I can show you is the result of our data, where for the first 2 hours, we have to actually heat up the experiment, because as I'll show you, you have to get it up to about 800 Celsius before you can produce the oxygen. Then we turn on the oxygen production, and we produced actually 6 grams of breathable, 100% pure oxygen. Over the course of about 2.5 years, we've run MOXIE 16 times. What we wanted to do, as I say, this is a demonstration of the technology. Mars' atmosphere is very variable. Its density over the course of a year and day-to-night cycles can vary by a factor of 2, much more variable than here on Earth. We have slight variations in atmospheric density, but on Mars, they're really significant, and we needed to demonstrate that we can make oxygen under all atmospheric conditions, during all seasons, during night and during day, and that's what we succeeded in doing. And sadly, in a way, but everything comes to an end. So in September of 2023, we turned MOXIE off because it had basically successfully demonstrated everything that we had hoped it would do. So how do we do it? Well, the first thing that we have to do is to filter out the dust from the Mars atmosphere. As I told you, there's a lot of dust in the atmosphere. We have a standard HEPA filter. That's the one part of MOXIE that's outside the rover. Then we have to compress the Mars atmosphere, which is very thin, before we can electrolyze it. And we do that with a scroll pump and a motor. And we then go into the solid oxide electrolysis assembly. It's a little bit like a fuel cell, only it runs in reverse. A fuel cell takes, well, a typical fuel cell takes hydrogen and oxygen, but you could also take carbon monoxide and oxygen, combine them into carbon dioxide and produce electricity. We do just the opposite. We use electricity to split the carbon dioxide into the carbon monoxide and oxygen. This is a schematic of what is inside that. This is the guts of MOXIE inside the electrolysis assembly. You can see there's 10 different layers, and each of those layers is a little electrolysis cell with an anode and a cathode, and a schematic diagram of each individual cell shows how the process works. So as I say, we take the carbon dioxide, we have to heat it up to 800 Celsius. There's a nickel catalyst on the cathode, and at those temperatures with the nickel catalyst, the carbon dioxide separates into carbon monoxide and oxygen negative ions. We then have an electrolyte which has a special crystalline structure such that it only permits the transit of oxygen ions, not electrons. And so we get pure oxygen ions moving through the electrolyte, finally ending up in the anode. And of course, all this requires electrical power to make it work because we're moving the electrons around, but those oxygen ions give up the electrons. They form into oxygen molecules, and the electrons continue to move around. For every amp that we put into the system, we can make about 3 grams per hour. So one of the things that you have to remember about electrolytic production of oxygen, or actually almost any type of electrochemistry, it requires a lot of electrical power. I'll talk about the implications of that shortly. We want to make as much oxygen as we possibly can, but we have to be very careful that we don't push it too far, because if we split that second oxygen atom off of the carbon monoxide, then we end up with pure carbon atoms, which in one of our laboratory experiments, you can see the result. It cokes up the electrolysis system, and then we are out of business. So we have to operate very carefully. There's a very narrow range of voltages, and again, I don't want to go into all the technical details, but when we run this in a laboratory, we have a big red button where if something isn't going right, we can just push the red button and everything stops and we're safe. We don't have that red button on Mars. I mean, it takes minimum of 10 minutes or so to get a signal to Mars, and but by the time we know that anything is going wrong, it's too late. So we have to program in a lot of protective software, and we have to operate very conservatively. But I'm glad to say that it worked. We never had a problem, and MOXIE was an incredible success. Due in a large part, of course, to the extensive laboratory work that was done. This was a joint project of NASA's Jet Propulsion Laboratory at MIT. The MOXIE experiment was built at Jet Propulsion Lab. Then they turned it over to us to operate and to do the science. So where do we get from MOXIE to getting Mark Watney home from Mars? We need to be able to scale up this technology by orders of magnitude in order to produce enough oxygen to fuel up a rocket. Just to give you an idea, because Mars goes around the sun every 2 years, 2 Earth years, and it turns out that every 26 months, Earth and Mars are closest together. And with our current rocket technology, that's the only time we can get to Mars. So every 26 months, we can launch missions to Mars. So the idea is, on one of those cycles, you'll launch the oxygen-producing equipment, you'll launch a return rocket, which will use all its propellant to land on Mars, and it will have an empty tank. At least the oxygen part will be empty. You do need a fuel, and we can talk about that later. Methane, carbon, and hydrogen, CH4. Obviously, we can get the carbon from the carbon dioxide in the atmosphere. That's all that MOXIE can do. To get the H, we would have to mine water. So someday, we will be able to mine the water ice on Mars and combine that with the carbon dioxide from the Mars atmosphere and make methane and oxygen, so you have fuel and propellant. But remember, the methane is only 1/4 of the mass of the propellant, so if we can just make the oxygen, we're still way ahead. And for the immediate future, that's probably what we'll be doing. Anyway, you land that, now you have basically a little bit over a year to make the oxygen that you need to fill up the oxygen propellant tank on the rocket. And we can calculate, again, you need the 30 tons of propellant. You need to be able to make about 3 kilograms per hour in order to fill up that tank in the right amount of time. Compared to, well, we averaged about 6 grams per hour with MOXIE. Our power supply was limited to 4 amps. And remember, I told you that 1 amp of current will give you 3 grams per hour. So the last few times we operated MOXIE, we demonstrated that we could operate it at full capacity, and we made a whopping 12 grams per hour. But that's a far goal from, the 3 kilograms. And the other thing, remember the electrical power you need. To make that amount of oxygen, you're going to need on the order of 25 kilowatts. We had about 120 watts available on the Perseverance rover, and we used it all. So we're almost certainly talking about some sort of a nuclear power plant, which ultimately I think is going to be necessary for human exploration. But the technology works. And in fact, the company that made the MOXIE electrolysis unit has already demonstrated, you can see MOXIE over here, and they've already made a much bigger electrolytic stack and have demonstrated that they are capable, if they have enough electrical power, of producing the amount of oxygen we would need for a human mission to Mars. So it's exciting, something to look forward to in the future. I want to end, though, with some comments about humans and robots. I know I always get questions, gosh, these rovers are doing such a great job. Why bother to send humans to Mars in the first place? Well, Perseverance, I mean, it's done a great job. There it is. It's very happy. But, it's an incredible machine. It has spectacular capabilities, but we're only able to operate it at a fraction of its capability. And why is that? Well, first of all, when you command it, we have to do it remotely. You can't joystick the rover in real time. So you have to plan ahead. You look at what the terrain is in front of you. You make up a plan. You program it. You send it up. All of that's going to take you over a day. And then the next day, the rover will execute the plan. And then you have to get the information back from Mars to show, did it actually execute the plan correctly? Because sometimes something goes wrong and it stops in the middle, and then you have to reconfigure. So just the amount of time it takes is you could reduce that tremendously if you had somebody nearby in real-time control. But more than that, we have to operate these rovers so conservatively. If they get stuck in the sand, there's nobody to dig them out. If the wheel breaks, nobody can change the tire. Also, suppose you are a planetary scientist and you come up with a really intriguing new idea for an experiment that you would like to send to Mars. You have to wait at least 26 months, but really you have to wait until the next rover is going to be sent, which at the rate we're going is like 10 to 15 years. Wouldn't it be great if these two guys were on the surface of Mars in spacesuits, and this was a rover which was designed to be modular? You could operate it in real time, go so much faster, so much farther, and you could operate it much more aggressively. If it gets stuck in the sand, you go and dig it out. If the wheel breaks, you change the tire. And if an experimenter sends you an experiment that they would like to put into the rover, assuming that you've designed the rover to be modular, you just take out an old experiment and you put in the new experiment. You get so much more utility out of a rover. That's why the Hubble telescope has been such an incredible scientific success. Every time, people think about, oh yeah, we fixed the focus. Well, that was the first thing we did. Obviously, you can repair things when they break, but we've had 5 servicing missions to Hubble. Every time we visited the Hubble Space Telescope, we take out old detecting instruments and we put in new, more powerful ones. Hubble now has almost 1,000 times more sensitivity than it did when it was first launched, even without the focusing problems. If we could do that with rovers and have humans and rovers operating together in the same environment, we would have a synergy where you could get so much more value out of humans and out of robots. So that's really my vision for the future of planetary exploration. Obviously, there are many places where humans are never going to be able to go, and I'm very happy to see our best robots go there. But in places where humans can go to explore, the synergy between humans and robots working together will give us a far, far greater ability to explore than we currently have. So I don't know when we're finally going to get to Mars, so please, during the questions, don't ask me. Elon Musk says he can get there 4 years from now. I wish him luck. I hope he's right. Maybe not, but someday we're going to get to Mars, and whether we do it on a capsule or with SpaceX's Starship, the one thing that I wish for my future astronaut colleagues when they finally do get to Mars is, please, ladies and gentlemen, do not forget your MOXIE. And with that, it's been a pleasure presenting this to you, and I look forward to your questions.